Today we're going to learn about determinants of matrices. There is the identity matrix, which we already know that definition. It is a square matrix. And there are a 2x2 matrix and a 3x3 matrix. The determinant of the identity matrix is always 1. So what is a determinant? Well, we can find the determinant of a 2x2 matrix with the following formula. And you can either show it as determinant of a matrix by writing the word det in front, or the determinant is shown sort of with absolute value bars. And the way that I remember the formula is this diagonal is positive, this diagonal, which goes backwards, is negative. So you do A times D, and you subtract B times C. It seems like in matrices, once we started matrix multiplication, we just started inventing all sorts of crazy rules. This is the rule for a determinant. And we're going to find out what a determinant does and how it's useful, but not yet. We always begin with just doing some math, learning how to develop the skill before we find out how this is useful. So on this one, for the determinant, you would get 8 on this diagonal. You would get a negative 9 on that diagonal. And if you did 8 minus a negative 9, you would add, so you would get 17. Someone who likes square matrices better than other matrices. And this one will be 36, and then we will subtract. And this is 36, so it's equal to 0. And I can tell right now that in the matrix in A, the inverse exists, whereas the matrix in B, the inverse doesn't exist. So the determinant helps us find out if an inverse exists or not.
If it's greater than 0?
Maybe. We'll have to find that out. You can only find the determinant of square matrices, and matrices that have a determinant of 0 are called singular matrices. And a singular matrix does not have an inverse. So it's only if it's 0 that it doesn't have an inverse. All other determinants, if they're non-zero, it'll tell you that that matrix has an inverse. So which is kind of leading into what we're going to do after determinants, is finding inverses. Here's a nice formula to remember. Okay? So where does that formula come from? Okay? If you take A and you ignore everything in that row and column and take the determinant of this, that gives you this part. Then you subtract. So then you take B, forget everything in that row and column, and then do the determinant of what's left. And then finally, oh, I should have underlined this one in green. And then finally, you take C, forget everything in this row and that column, and do the determinant of what's left. And you find the determinant of your 3x3. Now, if you extend what we did with the arrows for our 2x2, you know how I did this positive and negative? If you extend that to our 3x3, you can use this as a shortcut. So what we do is we rewrite the columns, the first two columns, A, D, G, and B, E, H. And you make 3 positive diagonals and 3 negative diagonals.
But why is only the first two? That's what works.
You need the first 2 in order to make 3 diagonals. Okay? If you want to think a little bit about why that works, okay, I'm going to add, actually, do the colors make sense there? Why did I switch them in the second one? Because there's a minus sign with the B. Now, if you're multiplying E times K, and then that gets multiplied by A, does that make sense that that matches up with AEK? And if I multiply F times H, and that gets multiplied by A, but the F times H is negative already, that will match up with this one. Similarly, if we look at the second one, we'll have negative B, but that B multiplies by F and G, so BFG. Isn't there a movie? Big Friendly Giant. It's positive, that's good. And if you do BDK, that matches up with that arrow. And finally, CDH matches up with this arrow, and CEG matches up with that arrow. So I like using this as a much easier way than trying to memorize that formula or think about all those things happening. I just rewrite my first 2 columns, multiply the positive ones, multiply the negative ones, add and subtract. So here I would rewrite 2, 1, 2, negative 1, 2, 1. And we would get 12 minus 14, which is equal to negative 2.
Show us how you do it the other way. With the E at H.
So if you wanted to do it the other way,
Yes.
okay, I'll just go. So if you wanted to do it the other way, the determinant of this matrix, I'm going to call it A, determinant of matrix A would equal, you would take 2 and multiply it by the determinant of 2, 1, 2. Then you would minus a negative 1 multiplied by the determinant of 1, 2, 0, 2. And finally add 4 multiplied by the determinant of 1, 2, 2, 1. So this will be 4 minus 0, right? Plus 1 times 2 minus 0, plus 4 times 1 minus 4 negative 3. So we get 8, 10, minus 12, negative 2. Did we have negative 2 last time? Whew. That would have been terribly bad if there was different answers. And a third technique, which also gives you a different answer. No. But I find, I mean, both of them aren't bad. Okay? As far as doing the work. But I find that drawing the arrows just seems easier to remember than using the 2 by 2 determinants. Where the magic's coming from. And so because we get an answer of negative 2, we know that there is an inverse for this matrix. So I'd like you to type this matrix into your calculator and see if you can figure out how to find the determinant using your calculator. All right, I like it when there's zeros, because then I always put a set of brackets here with a negative out in front, and then I'll go 0 plus 0 plus 12, and this way 12 plus negative 30 plus 0. So you get, in the end, 12 minus a negative 18, which is 30.